Welcome to Shanti-Peace for Mathematics. In this video, we are going to discuss about the alternating series. So far, we have considered the series with the positive terms only. Now, we shall discuss a series with the term having any sign whatsoever. So the definition of alternating series gives you a series whose terms are alternatively positive and negative. For example, the series 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 and so on. So this series is known as alternating series because the first term is positive, second term is negative, third term is positive, fourth term is negative. So alternatively, it is positive negative terms are appear here. So that's why this type of series is called the positive term series. In particular, the positive term series is always of the form n running from 1 to infinity minus 1 raised to n minus 1 an. So it is of this form. Alternating series are of this form where an is a positive sequence. Positive sequence means each of an is positive. Now, it is interesting to know that under which situation this alternating series are convergent and under which situation they are divergent. So for that we have one test for alternating series that is called Leibniz test. So the Leibniz test for alternating series which states like this: if the alternating series summation n running from 1 to infinity minus 1 raised to n minus 1 an, that is nothing but the a1 minus a2 plus a3 minus a4 up to so on, is such that satisfies the three conditions. This an should satisfy the three conditions. The first one is each an is positive for every n. The second condition, that is an is a decreasing sequence. That means an plus 1 is less than an for every n. Third condition is required that limit of n tends to infinity an is equal to 0. That means its nth term has to be tends to 0. If this alternating series satisfying these three conditions, then the series summation of minus 1 raised to n minus 1 into an is convergent. If any alternating series satisfying these three conditions, the first one is each an's are positive. The sequence an is a decreasing sequence and the nth term is tending to 0. Then the summation of minus 1 raised to n is convergent. And this test is called the Leibniz test. Let us try to prove this statement. So to prove that this series is convergent, we'll need to see what will be the partial sum of this series. So let Sn be the partial sum of this series. Sn is equal to a1 minus a2 plus a3 minus a4 up to so on plus minus 1 raised to n minus 1 an. This depends on what will be the value of n. And therefore, what we can see here, we note that if the value of n is even, let's say it is 2n plus 2, then you just observe that the last term that we have here, it will be minus sign. So that's why it will have a1 minus a2 plus a3 minus a4 up to so on. Let me write the last term. So that will be how having the minus sign, because of it is instead of n we have 2n plus 2. If I substitute here, it is 2n plus 2 minus 1. So it will be an odd number. So that's why it is a minus sign a 2n plus 2. Its previous term, it is a 2n, which is having a 2n plus 1, which is having negative plus sign, and its previous term, which is also having the negative sign, that is a to n. So this is the terms we have for s to n plus 1. Let me observe what is s to n. As in the similar argument, it is a1 minus a2 plus a3 minus a4 up to so on, it is minus a to n will appear. Now if I subtract this to equality or statement, will get s to n plus 2 minus s to n, will cancel out this a1, a2, a3 up to a to n terms will cancel out, only this terms will left. So it is left with a to n plus 1 minus a to n plus 2. Now we already note that what is given. The given that this sequence an is a decreasing sequence, because this value is always bigger than this one. So that's why this is greater than or equal to 0, because of the sequence an is decreasing. So this term is bigger than this term. So that's why this is. So from this what we can observe is, therefore s to n plus 2 is greater than or equal to s to n for every n. That means this sequence s to n, which is a partial sum, is monotonically increasing sequence. So it is really increasing sequence. Again, just observe what is s to n. As per the argument, I said that s to n is a1 minus a2 plus a3 minus a4 plus so on. It is plus a to n minus 1 minus a to n. Now let us observe this term. We'll have it is a1 minus, I'm just commoning out minus sign from this two, so it will written as a2 minus a3. Let us common out minus sign from the next term, that is a4 minus a5. And if you do this type of situation in each every term, we'll have the last one, it is minus of a to n minus 2 minus a to n minus 1, and this minus a to n is stay as it is. Now we already note that this sequence an is a decreasing sequence. So this term will be positive, this term is positive, this term is positive, and an is also positive. So this means all these terms are positive. So I can just write down this is a1 minus, I can write down this is a1 minus some alpha, where the alpha is equal to this quantity, that is a2 minus a3 plus a4 minus a5 up to so on a to n minus 2 minus a to n minus 1 minus plus a to n. So this is the value of alpha, that is this value which we have taken with minus sign. And this we note that alpha, which is we have here, it is a2 minus a3 plus a4 minus a5 up to so on a to n minus 2 minus a to n minus 1 plus a to n is positive, because the sequence an is a decreasing and each an is positive for every n. So that's why this alpha is a negative, because this is a positive term, a2 is bigger than a3, a4 is bigger than a5, so this is also positive, so it is a sum of positive numbers. So that's why this alpha is positive. And from the previous one what we can note, it is s to n is equal to a1 minus alpha. So I can say this is less than or equal to a1. For every n we can write this. Due to this alpha is positive, so we are subtracting some value from alpha. So we'll have this. So what we have noticed from this equation number 2 or inequality 2 and from the statement number 1. So for statement 1 says that this s to n is a monotonically increasing sequence, and this equation 2 says that s to n is a sequence which is bounded above. So thus from 1 and 2 we say that the sequence s to n is monotonically increasing and bounded above. And we know that any sequence which is monotonically increasing and bounded above, therefore the sequence s to n is convergent. Let us say it is converged to S as n tends to infinity. Let us say this. Now what we will prove, this is the sequence of even terms of that partial sum. Now we will prove that sequence of odd term, that is S2n plus 1, which is also converged to the same limit. So for that, let us observe what will be the S2n plus 1. Equal to, we know that it is A1 minus A2 plus A3 minus A4 up to so on. It will be minus A2n plus A2n plus 1 you will have. So what is this quantity? This quantity is S2n that we know, plus A2n plus 1 we can write, and that is S2n plus 1. If I take the limit both the sides, so therefore the limit of S2n plus 1 as n tends to infinity, that I can write down by property of limit is limit of sum is sum of limit. We will write that it is S2n as n tends to infinity plus limit of A2n plus 1 as n tends to infinity. But we already proved that the limit of S2n is S, plus we already have given that the limit of an is 0. So that's why this quantity is 0. This is because of limit of an is 0 as n tends to infinity. This is given in our hypothesis, it is there. So therefore what we can got finally is limit of S2n plus 1 is S as n tends to infinity. Previously we have proved that S2n is tends to S as n tends to infinity. Here we have shown that S2n is 2n plus 1 is tends to S as n tends to infinity. So therefore we'll have the sequence S2n and S2n plus 1 both converge to the same limit S. Therefore the sequence Sn is converged to S. Since the even terms are converged to S and odd terms also converge to S. So your original series is Sn is also converged to S. And that completes the proof of that the series, the alternating series summation of minus 1 raised to n minus 1 an and running from 1 to infinity is convergent if it satisfies three conditions. That means the first one is each an should be positive. The second condition, this an is a decreasing sequence, and the third condition, limit of an is tending to 0. Let us solve a couple of examples here to discuss the convergence of some alternating series. So that the series 1 upon 1 power p minus 1 upon 2 power p plus 1 upon 3 power p minus 1 upon 4 power p up to so on converge for p greater than 0. Let us see the solution for this. Here we observe that it is an alternating series, and here an is 1 upon n power p, that is 1 power p, 2 power p, 3 power p up to so on. And we need to prove that it is converged for p greater than 0. So let us consider the value of p which is greater than 0. Now you just observe that n plus 1 is always greater than or equal to n for every n. So n plus 1 power p is also greater than or equal to n power p for every n is there, because p is positive. And if I take the reciprocal, therefore we can have 1 upon n plus 1 power p is less than or equal to 1 upon n power p for every n which is greater than 1. So therefore an plus 1 is less than or equal to an for every n. So what we can say, this sequence an is a decreasing sequence. Since it is a decreasing sequence, it is satisfying the first condition. Also, a limit of an as n tends to infinity, that is limit of n power 1 upon n power p as n tends to infinity, which will note that it is 0. So it is satisfying the third condition also. and an is equal to 1 upon n power p is always greater than 0 for every n. Therefore, by Leibniz test, the alternating series summation 1 upon n power p and running from 1 to infinity minus 1 raised to n minus 1 converges for p greater than. Let us solve one more example. Discuss the convergence of the series. So first of all, here you should note that an is 1, 2, 3, 4, so it is n upon n square plus 1 and running from 1 to up to so. We know that each an is greater than 0 and the series is alternating series. The series is alternating because its sign is positive, negative and so on. So let us check what will be the limit of this series, that is limit n tends to infinity an, that is limit of n upon n square plus 1 as n tends to infinity. This is limit, if I divide by n square in the numerator and denominator, we will have 1 upon n upon 1 plus 1 upon n square as n tends to infinity, and as n tends to infinity this is 0 plus 1 plus 0, that will gives me 0. So nth term will goes to 0. The third condition, if you want to apply the Leibniz test, you have to check whether the series is decreasing. That will check what is an plus 1 minus an. An plus 1, if I replace instead of n with n plus 1, we'll have n plus 1 upon n plus 1 square plus 1 minus n upon n square plus 1. So if I take the LCM, we'll have it is n plus 1 square plus 1 into n square plus 1. If I multiply this quantity here, that is n plus 1 into n square plus 1 minus n. If I simplify this n plus 1 square, this will be n square plus 2n plus 1 plus 1. So this will simplify, and simplify this brackets will leads to n cube plus n. So it is an plus 1 minus an, it is n cube plus n, that is this n is multiplied to this one, 1 will multiply to both and it is n square plus n. Then here every term is of negative, that is n cube minus 2n square, that n is multiplied here, that is 1 plus 1 will become 2, so it is minus 2n upon, we'll have n plus 1 square plus 1 into n square plus 1. You just observe that n cube is cancelled out, the 1 n square is cancelled, and this 2n will also cancel. So the answer left is minus n square upon n plus 1 square plus 1 n square plus 1, which is negative. So therefore an plus 1 is less than an for every n. For the sequence an is decreasing. Since it is decreasing, it satisfies all the conditions of Leibniz test. So therefore the given alternating series summation of minus 1 raised to n into n upon n square plus 1 is convergent. If you want to prove that any alternating series is divergent, then you have to check whether any one of the condition is not satisfied. For example, if I want to check that minus 1 raised to n minus 1 into n is not convergent, then it should not satisfy any one of the three conditions. That means the first condition, we have limit of an is 0 as n tends to infinity. The second condition is an plus 1 is less than or equal to an for every n. That means it is decreasing. And the third condition, that each an should be positive. So here you note that an is n, but this an, limit of an is infinitive as n tends to infinitive. So that's why the first condition is not satisfying. Even the second condition is not satisfying. So this series, by this test, it is divergent. So I can say that therefore the summation of minus 1 raised to n minus 1 into n is divergent. So in that manner, you can check whether the alternating given alternating series is convergent or divergent. Thank you very much for listening. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye. Sayonara.